So we are discussing about the magnetic fields produced by a current carrying wire, where different cases we have considered. One is the magnetic field for a arc, and from the calculation of the arc we can calculate the magnetic field for the circle, for semicircle, or any curved shape which is in the form of an arc. And another thing that we have already discussed, that is the magnetic field for a long, straight, infinite wire, semi-infinite wire, and finite wire, that we have already discussed. Now on the basis of that, there are several problems, and these problems are very easy if you apply these formulas and properly determine the directions. So we will discuss one or two similar kinds of problems. First one is this one. We consider there is a straight, infinitely long wire. Like this. And you can consider that at this portion there is a bending to form an arc shape. This one is forming an arc shape. So this wire is not straight, partially straight, then curved, then again straight. This is the center of this arc. This distance is given r. Radius is of this arc is r. Okay. This entire wire carries a steady current I. Then you have to find the magnetic field at the center of this arc. Find the magnetic field at the center of this arc. Find the magnetic field at the center of the arc. So what we have to do? We have to split this entire wire into some parts and calculate the field for each part and then add them vectorially, because field is a vector quantity. So we can split this problem into three parts. Two parts are semi-infinite wire and one part is a arc subtending an angle pi by 2, at the center. So calculating the contributions from the three parts, we can add them vectorial to find the magnetic field. First part, consider this one. From infinity up to this point. So you are near one point, other end is at infinity. So this part will contribute like a semi-infinite straight wire. So what will be its contribution? Suppose B1, then I can write B1 equal to mu naught I by 4 pi r for the semi-infinite wire. Okay. Then this sector means what is the angle produced at the center? Pi by 2 by this arc. So for that, magnetic field V2 will be mu naught I by 4 pi r into pi by 2. That phi is pi by 2 here. Pi by 2. So I can cancel this pi and write this one as mu naught I by 8r. That is the contribution for this arc, which subtends an angle pi by 2 at the center. Okay. So in the last class we have discussed the formula for arc, that is mu naught I by 4 pi r into phi. Phi is the angle subtended. Here angle subtended is pi by 2. Then next part is another semi-infinite part. This one. You are at one end, other end is at infinity, so its contribution is same as that of first one. That is B equal to mu naught I by 4 pi r again. Now check the directions. B1, it is inward. B2, it is inward. B3, it is also inward. So all the three parts are inward. So at this point the resultant field is directed inward. So denoted by n circle cross. So what is the total field? I can calculate sum of these three. Just normal sum we can do because all are along the same direction. Then B1 plus B2 we can add and write mu naught I, B1 and B3. So mu naught I by 2 pi r plus mu naught I by 8r. Now if you wish, you can take something common, mu naught I common, r common, etc. 2 common and write it in separate format. But essentially you have to do these things. First, you have to split the circuit, split the entire wire into components such that you can apply the formulas that you have already derived. Okay, you have derived for straight finite wire, straight semi-infinite wire, straight infinite wire, and for any arc you know how to calculate. So split this entire problem into small parts such that you can identify which part is coming and which semi-infinite, which part is finite, which part is infinite, and apply the formula to write the magnetic field. That is the problem. Okay. So these problems are not that much difficult. Only thing that will be difficult that we will discuss. One of this sample in mock paper, that problem is there where you have to find the directions properly, because in these cases the directions are very easy. All the directions are along the same direction. So but we will discuss some other problems which are not so easy. Okay. Is this problem clear? What we have to do? We have to split the wire into small parts such that we can apply the formulas that we derived. And then accordingly I have to add it vectorially. Here vector sum is not required because all the components are along the same direction. Next problem. The direction of current is this one. This radius is given R. Find the magnetic field at the center of this setup. Find the magnetic field at the center of this setup. বিমানের ক্যালকুলেশনটা ঠিক নেই আর ফুটের আটটা বলেছে বছর ট্রেনগুলো ক্যান্সেল করতে প্রথমটা ভালো হবে So how many parts you can choose from this circuit? 3 parts. First one is a straight wire, second is an arc, then another straight. What will be the contribution of this one? Suppose P1 at the center. It will contribute nothing because the center is on that line and the direction of that line, center lies. So according to Biot-Savart law, that there will be no field on a point on the line. So for producing the field, this point must be outside the direction of this line. If it is on the direction of the line, then there will be no field. Because in Biot-Savart law, you find one theta, then that theta will be 0 if it is on the line. On the line, theta 0 means field will become 0. So on a particular current carrying wire, there will be no field for this particular wire. For different wire there can be a field, but for this particular it cannot produce any field on its own. Clear? So first part is 0. Now for the second part, suppose its contribution is B2 at the center. That I can calculate. What is contribution of B2? B2 is forming an arc. Then for B2 I can write B2 equal to mu naught I by 4 pi r into angle subtended at the center. Don't take this angle. This is the angle subtended at the center. Inner part in which the arc is formed. Arc is subtending an angle, not this part. There is no arc. So the angle is not pi by 2. It is 3 pi by 2. So pi cancels and it will become mu naught. So this is B2, mu naught I, 3 mu naught I by 8 r. And what is its direction? Inside. So this is the wire. So curve these fingers, it will go inside. So I write it in circle cross. Now last part, this one. This one is a semi-infinite wire because you are at the one end, other end is at infinity, and this point is not on this line. So it produces a magnetic field. So that magnetic field will be B3. It is mu naught I by 4 pi r. Contribution for semi-infinite. And its direction will be encircle dot. Check. This is the wire. So if you are going here, it will be inside. So at this point your other fingers are coming out of the board. In this way current is flowing along the thumb and this is coming out. So at this point B3's contribution is given by encircle dot coming out of the board. Now you have to do the sum. B2 and B3. Which one is higher? B2 or B3? B2 is higher. See, 3 mu naught is there and there is only mu naught in the numerator and in the denominator it is 8r. That is larger. So B3 will be much smaller. In the B3 there is numerator 4 pi. 4 pi is almost 12 point something. So it will be much less than the B2. So net field will be B2 minus B3. B equal to B2 minus B3. So it will be 3 mu naught I by 8r minus mu naught I by 4 pi r. And its direction, in that direction is again encircle cross because inward field is stronger than the outward field. B2 is stronger. B2 is higher in magnitude than B3. So net field will be B2 minus B3 and it points in the inward direction. Okay.
So can you explain the directions again?
Okay. See. For this current is along this direction, so put your right hand thumb along the direction of the current and rotate them. So inside at the center it is pointed inward. So V2 will be inward. Okay. For this one, this is the direction of the current. So put your thumb along. So rotate this one. So at this point it is going in. So at this side it is coming out. So V3 will be coming out. But V2's magnitude is greater than V3. So resultant field will be V2 minus V3. Okay. So the thing is that for the last part V3, consider this is the wire. Now it is the showing the direction of current. So at this point, suppose downward, it is going inward. Board is this one. Then when you rotate them, and it will come out of the board. But center is above the wire. So when it is rotating and coming out, so V3 will be coming out of the board. Okay. V3 coming out of the board. Because you have to consider them like this. So this is the wire, it is going here inside. So at the position of the center, it is coming outside. So that's why it is taken as out of the board. Clear? Now, next, this problem is in your mock papers and it is coming in the examination also, previously by Q actually. This one to try to draw it little large. Its radius is given r. Current is going inside, going in this path and then leaving this circuit like this. This one is a 3D diagram. 3D. Consider this wire in 3D. Like wires are actually like this. Into the board, then the wire is like this and then coming out of the board. Okay, so this is actually a 3D diagram. This is going, this wire is like this, wire is like this up to this point, then it is like this, then it is coming out of the board. So these two parts are actually coming like this. Okay, this one is 3D circuit. Now, for this, to find the direction of the magnetic field, you can do by elementary method, but it is better to use the unit vectors. Otherwise, you will face difficulty in finding the total magnitude. So, better to use unit vector to solve this problem. So, first, for applying unit vector, I use the Cartesian coordinate, 3-dimensional Cartesian coordinate. See. X-axis, Y-axis, Z-axis. can visualize the problem much better, because these two straight wires are along the x-axis and the arc is semicircular arc is in the yz plane. So these are perpendicular to each other. Now we have three parts. So for each part I will calculate the magnetic field separately. First calculate for the first part this one. Contribution of this field at the center. Let it be V1. So what is V1's magnitude? It's a semi-infinite wire because this side is at infinity and this side is given at one of the sides. So that is a semi-infinite wire's contribution. So what is semi-infinite wire's contribution? Mu naught I by 4 pi r. So write mu naught I by 4 pi r. Now what will be the direction of this contribution? It is like this. Which this wire is like this. So this thumb is showing the direction of the current, and at the center of the this portion, what is the direction of the field? Downward. Or over this plane, downward. So over this yz plane, that is the plane of the board, it is going downward. So what will be the unit vector? Opposite to z direction. What is the unit vector? Minus k cap, ijk. So it will be minus k cap. See, this wire is actually like this. So its contribution here will be downward. Downward means opposite direction of z axis. So I write here minus k cap. Then come to this contribution of second one. This one. V2. Check. This one is a semi-infinite part. Semicircle. This one is a semicircle. So for the semicircle, what will be the magnetic field at the center? Mu naught I by 4r. Because mu naught I by 4 pi r into pi. Pi is the angle subtended. So pi cancel. It will be mu naught I by 4r. So first write the magnitude. Mu naught I by 4r. So I consider it capital R. So check all this capital R. The direction, it is coming out of the board. So at this point, these fingers are showing the direction downward, over the board, downward. Means again opposite to the z direction. Now add them and find the answer. So V1 and V3 can be added directly. So I can write V equal to mu naught I by, first I write V2 by 4r minus I cap plus mu naught I by 4 pi r minus 2 k cap. Okay? So I haven't changed mu naught I to mu naught I by 2 pi r. I keep that 2 with the unit vector. Done. Now I can multiply this numerator and denominator for this part with pi, such that I can write it in this format. Mu naught I by 4 pi r into minus pi I cap plus mu naught I by 4 pi r minus 2 k cap. Okay. Now can I take mu naught I by 4 pi r common from both and finally write B equal to minus mu naught I by 4 pi r. This entire thing taken common. Mu naught I by 4 pi r. And minus sign is also taken common. Then inside the brackets, the term will be pi I cap plus 2 k cap. That is one of its in your mock paper. It is a previous year question. So this form you have to identify. There are 4 formats given. So correct format is this one. Mu naught I by 4 pi r pi I cap plus 2 k cap with a minus sign overall. First part, it is like this actually. Okay, so this is a semi-infinite part because you are at one side, so current is there. So magnetic field at the center will be directed down. Down means negative direction of z-axis. For this portion, another straight part, it is also semi-infinite because you are at one end. Current is coming down, so field at this portion will be directed down. So both of these parts will have the same unit vector, that is minus k cap, and this arc semicircle. So put the thumb in the direction of the current. So at this point, these other fingers are going inside. So that is minus negative direction of z axis means minus I cap, and then you add vector here. Now, if it is asked in this problem to calculate the magnitude of the field, net field, what you have to do? You have to individually calculate this pi here, individually multiply these two here, and then you have to calculate both the magnitude square and then add and then root. Like bx square plus by square root will give you b. Root over of bx square plus by square. So same method you have to apply here to find the resultant magnitude. But otherwise, you can keep in this vector form and always try to calculate this type of problems in vector form. Because if the where is set up is given in one dimension, then there is no use of the vector form because either the field will be inward or outward. You can simply add them with positive and negative, calculating, you can add them. But if this is a 3D setup, then the field may be in different directions. So as a result, it is not so easy to calculate with the elementary method with that keep track on this details along x-axis, this field along. So you cannot get only plus and minus. Such that inward and outward this is not there. This may be in any other direction. So for keep track on this problem, you have to use the vector. Otherwise, it will be very difficult to solve this problem. Okay. Now, see, this is the entire wire. This solid curve is entirely the wire. These are the center. radius r. This is the center. And it is given that the entire wire is of uniform area of cross section. The area of cross section is uniform of the wire. Whatever be the parts of the wire, this part, this part, this part, all parts have the same area of cross section. A current I is going through this wire and leaving the finally through this setup. Find the magnetic field at the center. Find the magnetic field at the center. Find the magnetic field at the center. The circle. You cannot calculate directly by using the formula of the circle, because for the circular part you cannot use mu naught I by 2 pi, mu naught I by 2r. Why? We know that in a circular loop, if I current flows, then at the center field will be mu naught I by 2r. But you cannot calculate with that formula. Because in the entire circular loop, same current is not flowing. After coming to this point, this current is branched into two parts and meet here like parallel combination. So in this part and in this part, current flowing is different. Because this portion has a longer length, so larger radius. Larger radius means in parallel combination small current, and smaller radius means large current. So current in the two parts are different. So you have to calculate the contribution separately like R. And finally I will tell you one trick to solve this problem. This is a one-liner problem. Please want to consider line. Please for consider line how can it be same? Because this is divided into parts. So now this constant, this one as a resistance, these are the resistance, so this one is another. So you have to find the current accordingly, how much current flows here, how much current. Then you can calculate. So there are, and you have to calculate actually the four parts. As the four parts. First part is obviously 0 because it is on the line. The second for the circle is actually divided into two arcs because two arcs are carrying different currents because they are in parallel combination and their resistances are different. Y shape. So let us consider in this the current I1 flows through this, and after branching current I2 flows here, and again they will meet to form the total current I according to Kirchhoff current law. Current is divided into two parts, then again they will meet to form the total current. Now, since these two parts are in parallel, so potential difference across them are same. Across any parallel combination, potential difference equal to constant. Now, since potential difference is constant, I can write I1 into, suppose it has some radius, I1 R1 should be equal to I1. Okay, I1 R1 should be equal to I1. Now, I mentioned that area of cross section is same. Then resistance is proportional to length, because R equal to rho L by A. So, if area of cross section is same, then resistance is directly proportional to the length. So, I can write I1 by I2 equal to simply R2 by R1, and in place of R2 and R1, I can put their lengths only, because area of cross section constant, resistivity constant, so all those constants will cancel. Resistivity constant, area of cross section constant, so all those parts will cancel, and it will become R2. What is the length of R2? This part. It is total circumference by 1/4 of the total circumference, and this one is the 3/4 of the total circumference. If this circle has circumference 2 pi r, so this is 1/4 of the 2 pi r, and this length is the 3/4 of the 2 pi r. So accordingly put R2 is 2 pi r by 4 divided by 3 into 2 pi r by 4. So actually 2 pi r will cancel, 4 will cancel, so it will be 1 by 3. So you are getting I1 equal to 3 by 4 I2. Sorry, 1 by 3. I1 will be this, all this cancel, so I1 will become 3I. 3I. I2. Okay. This I1 will become I2 by 3. Done. Since resistance is directly proportional to length, because area of cross section remains constant, so we can do this. Now, what is the total current? I, that is I1 plus I2 equal to I. So write this one. I1 is I2 by 3 plus I2, that is equal to I. So it will be 4I2 by 3 equal to I. So I can write I2 equal to 3I by 4. So immediately I can write I1 equal to I by 4. I2 is coming 3I by 4, so I1 will become I by 4. So once again check the calculation. Since they are in parallel, so I write I1 R1 equal to I2 R2. So I1 by I2 equal to R2 by R1. R2 means this part. That is 1/4 of the circumference. So that's why I write 2 pi R by 4. And then this part will be the 3/4 of the circumference. So I write 3 into 2 pi R by 4. So then 2 pi R by 4 will cancel. So I1 will be equal to I2 by 3. I1 will become I2 by 3. Then we know that I1 plus I2 equal to I. So I put I2 by 3 plus 1 equal to I. So it will become 4I2 by 3 equal to I. So I2 is getting, I am getting 3I by 4. So if I2 is 3I by 4, then I1 will be I by 4. Okay. Now we can proceed for this calculation. Now first part contributes nothing. This part contributes suppose B2 and this part contributes B3. This part contributes B4. So we will calculate individually. So what is B2? B2 is an arc that is mu naught I1 by 4 pi r into what is the angle subtended? That is 3 pi by 2. So put 3 pi by, so this pi will cancel. So what is coming? 3 mu naught by 8r into I1. What is I1? I by 4. So if you put I1, this will become 4 into 8 means 8 into 4. So it will be 32. Okay, because it is initially 3 mu naught I by 8r. Now I put I1 equal to I by 4. So it will become 3 mu naught I by 32r. Now calculate the 3. It will be mu naught, another arc, mu naught I2 by 4 pi r into what is the angle? Pi by 2 for this lower arc. So cancel this pi. Now what is I2? 3I by 4. So put it here. 3I by 4. So it will be 3 mu naught I by 32R again. 3 mu naught I by 32R again. Means same. Okay. So how these are coming same? Because this is a longer arc carrying small current. This is a shorter arc carrying large current. So the contributions will become same. And check the direction of this contribution. B2 inward, B3. So together these two produces nothing. So whenever this type of parallel combinations are given, where it is mentioned that the area of cross section is constant, you can always consider that at the center for these two parts, magnetic field will be 0. So it is only a semi-infinite contribution, and that is the answer. So final answer will be this one only, that is B4, mu naught I by 4 pi r, and directed outward. This one at the center coming out. That is only the answer. So you have to remember this one for this calculation, that whenever there is a parallel formation will be there, and if there is a circle, in the circle by connecting the current at the two ends, whatever be the parallel combination formed, and if it is mentioned that area of cross section is same, then the magnetic field produced at the center for this entire parallel setup will be 0. So you can simplify the problem directly. So remember this point, this will help you in regarding problem solving, because in the exam you don't have that time to calculate. So you have to use this technique to eliminate those portions at the beginning. Once you see, you can eliminate and solve the answer for just taking one contribution for the semi-infinite case. This is actually a very easy problem, but concept behind it is much more. Okay. So initially you thought that this was not a NEET level problem. So many calculations are, but actually no calculation is required for solving the problem. Understand? So, now. Now we will discuss another part of this electromagnetism topic, that is how a current carrying wire or a current carrying loop will experience force if it is placed in a magnetic field. Because earlier we have discussed the magnetic force on a moving charge when it is placed in a magnetic field. So from that I can write force on a moving charge F equal to Q into V cross B Okay. Now, if the current is flowing through a wire, means charge particle is moving through the wire, I consider that the charge particle in time t moves a distance L, moves a distance through the wire, that is L. So velocity of the charge particle can be written as L by d, because we are considering steady current. Steady current means charges are flowing with constant velocity, that is the drift velocity. So I can write this one as Q into L by T into V. So I can write this one as Q by T as I into L cross V, and this will give you the formula for calculating the magnetic force on a current carrying wire. So because IL is the current element and when it is placed in a magnetic field, it will experience the force IL cross V. So now if any magnetic field is given, I will calculate IL cross V to calculate the force on that wire. Okay. Now, if I consider a very small element, then what we have to do? Since we are considering steady current, this I can be taken out and this can be written as DL cross B. DL cross B. Because all the time it will not the straight wire or anything. That's why you have to split it into small parts of the element that is considered to be straight, that is DL, then DL cross B, and you have to integrate to calculate the entire force. Okay. Now, first, suppose there is a magnetic field. and this is the current carrying. Can you loop anything? A loop in the magnetic. Current is flowing through this loop. Steady current I. This magnetic field is B, and it is given that this magnetic field is uniform. This field is uniform, both in magnitude and direction. Then, what will be the force on this loop? What will be the force given by magnetic force on this loop? How to calculate? Entire length of the loop you can consider L. Then what is the force on the loop? Nothing. Zero. Force on this loop will be zero. Okay. How? I can show you two methods to find that this force is zero. First one is straightforward mathematical technique. See, I equal to dl cross d. Now since this one is a closed loop, I can put a closed symbol. Okay. So this integral is a closed integral such that you can complete the loop. Now what is dl? dl is a small element of this current carrying wire, right? This part, suppose this length is considered as dl. Here, this small part of the loop is actually considered as dl, which is carrying the current. That's why IDL is called the current element. Now, this b is constant, so I can take this b out of the integral. I can take this b out of the integral since it is constant, but I cannot write it b integral dl because it is a cross product. So you have to write it in this manner, I, then closed integral dl. So you can, and this is a separately calculated. Then you have to take the cross product with b. Means now b is out of the integral, but I cannot write b in front. Then I have to write minus of b cross integral dl because cross product is anti-commutative. Remember, so if you try to write b outside, then you have to write in this form. Check I minus I b cross closed integral dl. In this method you can write, because it is dl cross b, not b cross dl. So if you write b in front, then you have to put a minus sign, because a cross b equal to minus b cross a, remember. So otherwise you can write like this. Okay. Now we are interested in calculating this part only. Now first part is a dl. Next we can consider another such dl, then another such dl, another such dl, 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 all such dl. So when we will come back, completing the loop, you will come back to this point. So how many vectors are there? Small displacement vector dl, infinite number, but all of them are taken in same order. So what will be their resultant? 0, because it starts from a point and come back to the same point. So the total displacement is 0. So entire result will be 0, because dl is a vector. So all such vector, when you use the triangle rule, in 3 sides all are taken in order, what is the resultant vector? 0. The same logic is applied here by taking the polygon rule. Small part, small part, small part, all are taken in order. So total sum will become 0. Instead of 3, you can take 4, 5, 6, 7, 8. You can take many. You can take infinite number, but it will coming back to the same point, because you are taking closed integral. So it will become 0, and magnetic field on this will be 0. Sorry, magnetic force on this will be 0. So for any current carrying loop, irrespective of its shape, if it is present in a magnetic field, force on this, magnetic force on this will be 0. So write this one. Any current, steady current carrying loop, steady, remember, any steady current carrying loop present in a uniform magnetic field, any steady current carrying loop present in a uniform magnetic field will experience no force, will experience no force. Okay? Now, another method I will tell you. Suppose, forget about all these things. Just consider electric dipole. Plus Q minus Q. Okay? Present in a uniform electric field. What will be the total force on the dipole? 0. Because QE in this direction, QE in the opposite direction. Because positive charge will feel the force in the along the direction of the field, negative charge will feel the force opposite to the field. Both forces are of same magnitude but different opposite direction, but their line of actions are not same. So net force still 0, but since their line of action are not same, net torque is not 0. So the dipole in a uniform electric field will only feel torque, not force. Same thing it is in magnetism. Any current carrying loop is behaving like a magnetic dipole. So when placed in a uniform magnetic field, net force on the magnetic dipole will be 0. Only the net torque will be there and loop can rotate. Okay. So it is a direct analogy with the electric field. Any current carrying loop is behaving like magnetic dipole, just like a bar magnet. And since it is behaving like a bar magnet, it is a dipole, and net force in a uniform electric field, a uniform magnetic field will become 0 always. So write down, any current carrying loop will behave like any current carrying loop will behave like a magnetic dipole. Will behave like a magnetic dipole. Okay? So in a uniform magnetic field, it will not experience any force. It will not experience any force. Okay. Now, any current carrying loop, how it is a magnetic dipole, that we will consider. Check. I have earlier calculated magnetic field for this circular current carrying loop at the center. We have calculated this one, radius r, carrying current I. Fine. So for this, what is the magnetic field at the center? Mu naught I by 2r. Okay, mu naught I by 2r. Now I want to change this setup a little bit. Mu naught by 4 pi into 2 into I into pi r square by r cube. Check whether I can write this one in this format or not. Cancel everything and see whether it is coming mu naught I by 2r or not. It is coming? Because all this pi can be cancelled, 1r can be cancelled, 2 can be cancelled, so it will be the same form. But now I can write this one as mu naught by 4 pi into 2 into current into area divided by r cube. Area of this loop is pi r square, and current into area is called magnetic dipole moment. So it can be written as mu naught by 4 pi 2m by r cube. Okay, so it is similar to the expression of an electric field. Dipole for a electric field for a dipole, 1 by 4 by epsilon naught 2p by r cube. Sorry, this vector is this is the magnitude of the electric field for a dipole on the axial position, that is 1 by 4 pi epsilon naught 2p by r cube. It has the same analogy. Mu naught by 4 pi is that constant, 2 into m by r cube. So m is considered as the magnetic dipole moment. Here p is called the electric dipole moment, m is called the magnetic dipole moment. Okay. So any current carrying loop, here we consider circular, but it may not be circular, may be elliptical, may be of any shape, maybe square, maybe rectangle, maybe triangle. It should be a loop, closed loop. If it is a closed loop, it will behave like a dipole, means just like a bar magnet. So that's why for any loop, the setup of the magnetic field lines, and for bar magnet, the setup of the magnetic field lines are exactly same. And for the solenoid, it is composed of so many loops, and each loop is behaving like a bar magnet. So the magnetic field of a solenoid and bar magnet are same in structure. Okay. Now, we can find one thing from this. Let us consider a situation that hydrogen atom. In hydrogen atom, electrons are revolving around the nucleus in a elliptical orbit, but with a certain approximation, I can consider them almost like a circular orbit. This is the electron. This is the positive nucleus, that is proton. This minus electron is revolving. Let us consider electron is revolving with a constant speed v, and then we can consider that time period of revolution of the electron will be 2 pi r by v. Correct? Time period of revolution of the electron will be 2 pi r by v. Then, what will be the current for this revolution of the electron? Electrons are moving means actually current. We can consider it is a current carrying loop. Electrons are moving in circular orbit, so we can consider it is just like a current carrying circular loop. So I can write this current as charge of the electron divided by time period of revolution, E by T, charge per unit time, that is called current. Then I want to calculate the magnetic moment for this electron, for this loop. For this loop, current carrying loop, it will produce a magnetic moment. So I will calculate this magnetic moment like M equal to current into area. So what is that current? E by T into area of this loop is pi r square. Area of the loop is pi r square. Okay. Then put the value of T that I have calculated here. It will be E by T means 2 pi r divided by V. So V will be in numerator. Then pi r square. Pi will cancel, 1 r will cancel, and it is coming EVR by 2. This is the magnetic moment of an orbital electron. So due to electrons rotation, electrons have some magnetic moment. This will lead you to certain numbers. Magnetic quantum number. Studied in chemistry for quantum number. Principal quantum number, azimuthal quantum number, spin quantum number, and for orbital angular momentum, magnetic quantum number. So this is that magnetic moment is there. So analogous to that, there will be a quantum number which is called the magnetic quantum number. Now, this is the magnetic moment of an orbital or electron. Clear? Now use Bohr atom model. What says in Bohr atom model? MVR equal to NH by this is the Bohr's first postulate. MVR will be equal to NH by 2 pi. That is angular momentum of an electron in a stationary orbit will be integral multiple of the quantity h by 2 pi. It cannot have any arbitrary value. And this orbits which satisfy this condition is called the stationary orbit. Means electrons can move in that orbit without radiating energy. electromagnetic radiation, because that is actually the when Rutherford model was predicted, Rutherford considered the electrons are orbiting, and then classical electromagnetic radiation says that if it is moving, it has centripetal acceleration that we have done in cyclotron, that there will be continuous radiation, so radius of the electron is losing energy, so its radius will decrease, and it will after some time fall on the nucleus, and that is a complete destruction of the electronic structure. But actually the electronic structure is very stable. So that's why you have to consider the Bohr model. The Bohr corrected this model by saying that there are some specific orbits. If the electron stays in those orbits, so it rotates in that orbit, it will not radiate any energy. So it will not obey the classical electromagnetic radiation concept at that time, because now it is the quantum model. And this quantization will be there, which says that angular momentum cannot have any arbitrary value. It will be quantized in the unit of h by 2 pi. Then from that we can write V into R equal to Nh by 2 pi m for Bohr model, and I will substitute it in place of Dr. So it will become E by 2 into Nh by 2 pi m. Nh by 2 pi m, where m is small m is the mass of the electron. Now you can write this one as n into Ph by 4 pi m. Ph by 4 pi m. Okay. Now EH by 4 pi m is entire thing is a constant. E is constant, H constant, M constant. So again it is showing that angular momentum of an orbital electron or magnetic moment of an orbital electron cannot have any odd value. It should be an integral multiple of this quantity EH by 4 pi m. Like angular momentum, magnetic moment of the electron, orbital electron is also quantized. Not only angular momentum quantization is there, Bohr model will directly lead you to the quantization of magnetic dipole moment also for the electron. Now this quantity is the value of the magnetic moment of an orbital electron when the electron is present in first Bohr orbit, that is n equal to 1. This quantity is termed as n into mu b. This mu b is termed as Bohr magneton. Bohr magneton. Write down, this mu b is the Bohr magneton. Mu b stands for Bohr magneton. Its value is EH by 4 pi m. Now write down, mu b is the unit of magnetic moment, unit of magnetic moment of an orbital electron. Mu b is the unit of magnetic moment of an orbital electron. So how it is considered as the unit, basic unit? Because if it is in orbit, first orbit, so n equal to 1, so the magnetic moment of the electron will be mu b. If it is in second Bohr orbit, then it will be 2 mu b, then 3 mu b, 4 mu b, so on. But it cannot be a non-integer of mu b. It should be an integer, because 1.5 mu b is not possible. Okay. Take a small break. Then we will continue again. So we have already discussed this Bohr magneton and orbital magnetic moment of an orbital electron. Now we will calculate the force between two parallel current carrying wires. This one we consider an infinitely long parallel current carrying wire. There is another parallel current carrying wire like this that is also infinitely long, and we consider that both are carrying the current in the same direction, I1, this is I2. Then what will be the force between them? That we want to find. Now we can consider that first wire is producing a magnetic field. First wire is producing a magnetic field, and second wire is present in that magnetic field. So I can consider that second wire will experience a force due to the presence of the magnetic field of the first wire. Similarly, you can also consider that second wire produces a magnetic field and first wire is feeling any force for the magnetic field of the second wire. So first I consider only the one is producing magnetic field. So let us consider this distance is R. So what will be the magnetic field for this wire at the distance R? Mu naught I by 2 pi R, because it is an infinitely long straight wire carrying current I1. So magnetic field at a distance R from the wire, at a perpendicular distance R from the wire, will be mu naught I by 2 pi R. So this field at this point is written V1. Okay, so I write the magnitude of V1. So V1 will be mu naught I1 by 2 pi R. Okay, mu naught I1 by 2 pi R. Clear? Now, what will be the direction of V1 at that point inside the board? Because I1 is here, so at this point it is going into the board. So I denote its direction at this point by encircle cross V1 vector. Now consider a small portion of the second wire. Small portion of the second wire. This one. Small portion of the second wire. It is considered as DL. So its direction is along the current, because any current element has the direction along the current. So what will be the direction of DL? Along current, that is I2. Now I can write that magnetic force on this small part due to V1 will be dF, that is equal to I2 dl cross V1, right? IL cross B. I am following the same law, that is I2 dl cross V1 will give you the magnetic force on this small part. Now, what is the direction of I2 dl? Place your these four fingers along the direction of I2 dl. Okay? Then what is the direction of V1? Inside the board. Then I2 dl cross B1. So what your thumb shows? Towards this. Means this wire, second wire is giving a force towards the first wire. Means first wire will attract the second wire. First wire will attract the second wire. Okay. So again, check the direction. I2dl is here along the current. Then V1 is inside the board. Thumb will show the direction. And in this direction, what is present? First wire. So first wire is attracting the second wire. This is I2dl. V1 is inward. So your thumb will be along this. So force felt by this wire will be along this direction. Means which one is present here? First wire. So first wire will attract the second wire. So I write here the force on this second wire, dF, this part of the second wire will be dF, and it is directed towards the first wire. Okay. Now, I want to calculate its magnitude. What is the angle between IDL and V1? 90 degree, because DL is over this and V1 is inside. So angle between them is 90 degree. So I can write its magnitude as DF equal to I2dl into V1 into sin 90. I2dl V1 sin 90. Okay, now I2 dl. What is V1? Mu naught I1 by 2 pi r. So you can write dF dl that is equal to mu naught I1 I2 by 2 pi r. That is the force per unit length of the second wire. Force per unit length of the second wire due to the field of the magnetic field produced by the first wire. Okay. So in this case you can see that two wires will attract each other. So if the wires are carrying currents in the same direction, that is called the parallel current carrying wire, they will attract each other. If the currents are in opposite direction, they will repel each other. So write this one, this point. Two parallel current carrying wires will attract each other, whereas two parallel current carrying wires will attract each other, whereas two anti-parallel current carrying wires will repel each other. Okay. And this is the force per unit length of the wire 2. That is mu naught I1 I2 by 2 pi r. If you calculate the force per unit length of the first wire, the same value will come. Now see, you cannot calculate the total force. You can only calculate force per unit length. Because if you try to calculate total force, then you have to multiply this dl here and integrate. And since these are infinitely long wires, integral TL will be infinite. So what is the total force on each wire? Infinite. So that is not possible to calculate. We can only calculate here force per unit length. Okay. From this one, actually you can give the definition of ampere, 1 ampere. That definition is coming from this form. But those definitions are not required now. You have to remember this one such that you can calculate any problem regarding this formula. You can directly use this form. Okay. Now, next we will discuss one problem. From this straight current carrying wire, there is a straight current carrying wire, infinitely long, carrying current I. There is a square loop of each side A. It is also carrying current I. The center of the square is at a distance x from the straight wire. What is the net force on this loop? What is the net force on the loop? Current carrying loop. It is present in the magnetic field of the straight wire. Because straight wire is producing a magnetic field, and we consider that the loop is present in the field of the straight wire. Then what would be the net force on the loop? Previously, what is the net force on a loop in a magnetic field? Zero, that we have derived. So what is the net force on this loop? What? Zero? No. Previously the magnetic field was uniform. Now it is not uniform, because as you are going away from the straight wire, the magnetic field will decrease. So this is a non-uniform magnetic field. So in that case it is not zero. Previously the magnetic field was uniform. You have to use the formula that we derived in the just previous problem. From that we can calculate. In the last problem we have calculated force per unit length, because that is not a I2 is not a finite well, it is an infinite well. But here I can consider 4 parts. Check. This is suppose W1, Wx, W is there, W1, W2, W3, W4. Okay. So what is the force on part W1, W2? That I can calculate now. Force part, let us consider force on this part. So these two are parallel current carrying where? Same direction. So this will be attracted. So this part will be W1, W2 will be attracted because both are carrying current in the same direction. So for this part, if the force is F1, I can write F1 by force per unit length. What is the length? Small a. That is equal to mu naught I1, I2. Both are I. So it will become I square by 2 pi. This distance from this point to this part. What is this distance? X minus a by 2. X minus a by 2. Then we can calculate F1. So F1 is this force. It is directed along this, right? So it will become mu naught I square a by 2 pi x minus a by 2. So this is on the first part, on which I mentioned here W1, W2. Then I want to calculate the force on W3, W4. Just opposite part. Let us consider in which direction this part will feel force. F2. So these two are original well and this part of the loop are carrying current in opposite direction, means anti-parallel. So they will repel each other. So now we can calculate similarly F2 by A. This is equal to mu naught I square by 2 pi into x plus a by 2. Means F2 will become mu naught I square a by 2 pi into x plus a by 2. This is for W3, W4. Now which force is stronger in magnitude, F1 or F2? F1, because F1 is close to the wire. So field is stronger there. So that force is larger. So what is the net force? F1 minus F2. Calculate. So that F1 minus F2 will give you the net force on the loop. Okay, so take two parts. One is parallel, the close one is parallel, the farthest one is the anti-parallel. So parallel wires will attract. So first part is, nearer part is attracted, the rarer part is repelled. Nearer part is feeling more force than the rarer part, so net force will be F1 minus F2. So the loop will be attracted towards the current carrying wire. So we use the formula for force per unit length, and since now the length of the small part of the square loop is finite, so I can directly multiply it. Okay? Then one question can be raised. I have calculated the force on W1, W2 and W3, W4. But on W2, W3 and W4, W1 I haven't calculated force. Why? Both will cancel each other. Not each part is feeling zero force. W2, W3 is feeling a force. W4, W1 is also feeling a force. But the forces are oppositely directed. If you calculate the force on this part, larger, smaller, medium, and this portion, similarly larger, medium, smaller. So as you are going far away, the force will drop, decrease in value. But overall, this force will cancel this one will cancel this one will cancel this one. So overall, these two parts will contribute nothing. These parts will contribute nothing. So only part that is contributing is this one and that one, because there is a mismatch of this force. Because the magnitudes are not equal for F1 and F2. So other two parts of force we can cancel in this manner. So because each pair will cancel each other, but for W1, W2 and W3, W4 there is no cancellation because the magnitudes of the forces are not same. So we have to calculate the resultant force, and that is F1 minus F2. So the resultant force is towards the wire. So entire loop is attracted towards the wire. Okay. If instead in the loop the direction of current is reversed, then the loop will be repelled from the wire. Now, Okay. There is certain ammeter setup and all these things are given, and I consider this one is present in a uniform magnetic field. So there are two poles of the magnets are taken, and we consider this one is present in a uniform magnetic field. Okay? Now, in this setup, a current will flow through this. This is a rectangular loop is taken and it is placed in a magnetic field. Uniform magnetic field we consider, and magnetic field is directed along this B. In the entire region this field is there. B. Okay. In the entire region between the two poles, the magnetic field is constant and it is considered as B. Now, there is a current flowing through each part of the wire. So, I will denote those currents at I. There is also I. There is also I. Now, consider this part of the length is L and this part of the length is small b. So, length and breadth of this square loop, the rectangular loop is taken as L into L and B. Okay. Now I can consider that this part is just like a, so I will put a name for this part, PQRS. PQRS. Now PQ is a current carrying wire present in the magnetic field. So I can consider that PQ will experience some magnetic force. PQ, individual part, is a straight wire and it's not a loop. If you consider only P2Q, then it is not a loop. So it will experience some force. So I can calculate this force. What is the magnitude of this force? Force on PQ, let us consider it F1. So its magnitude will be IL cross B, IL cross C, sine 90, because IL and magnetic field, these are perpendicular to each other. See, IL is along this and magnetic field is along this direction. So the angle between them is this one, that is 90 degree. So sine 90 will come, sine 90 will be 1. So the force on this part will be ILB. What is the direction of that force? Check. First you place your fingers along the direction of I. Okay. Then to rotate them in the direction of B, north to south. Your thumb will show the direction inside the board, right? Inside the board. So this is, don't think this one as a 3D diagram. It starts to rotate. Because this portion is giving a force in upward, this portion is giving a force downward, so it will rotate like this. Okay. Now, in this case, the energy given by you is the electrical energy by this battery such that current is flowing in the rectangular loop, and in the presence of the magnetic field this electrical energy is converted to which energy? Kinetic energy. That is mechanical form. And the loop starts to rotate. So this is by supplying electrical energy, you can convert it to mechanical energy. So this is the principle of DC motor. DC motor works on this principle. DC motor is a device in which electrical energy is converted to the mechanical energy. So any motor, like this fan, it's a DC motor because you are supplying electrical energy. Inside there is a toroid shaped coil which produces a magnetic field, and as a result there is a loop also, the armature coil. So this armature coil is a rectangular loop and it is present in the magnetic field of that toroid, and which will immediately on passing the current it will start to rotate, and that rotation is the rotation of this fan. So this write down, this one is the principle of DC motor, that in the presence of magnetic field electrical energy supplied to the loop is converted to the mechanical energy. The same principle is used for galvanometer. Galvanometer is same. Magnetic field is produced and there is a loop, and it will, on passing the current, it will rotate. And due to from that rotation, you can measure the amount of current. Galvanometer, DC motor, all are based on the same principle. Now, think about a different situation. If I remove this battery from this one, will the coil rotate? No, because current is not there. So if current is not there, then force is not there on each part. So torque will not be produced, and as a result it will not rotate. Now let us consider a situation, disconnect the battery and join these 2 points. Battery is not there. Battery is not, remove the battery and join those 2 points directly. It will not rotate. Now think about a mechanism by which you will start to rotate this one by your hand. External mechanism start rotating this one. What will happen? Now magnetic field is there and you are supplying the kinetic energy, that is mechanical energy, on your own. So immediately you will find that this ammeter will show current. So kinetic energy provided by you is converted to electrical energy. That is the mechanism of generator. Mechanism of generator. Just motor and generator, just the reverse rule. If you supply electrical energy in the magnetic field, it will start to rotate and produce the kinetic energy. That is the motor rule. Instead of any battery, if you provide kinetic energy for rotating it, then in the presence of magnetic field, it will generate a current. That is the rule for the generator or dynamo. Works on this principle. So you have to supply the mechanical energy from outside, and magnetic field will convert this mechanical energy into electrical energy. Just opposite to this one. Now, what actually happens if you rotate this one in the magnetic field? There are so many magnetic field lines due to the magnetic field, and you are rotating this. So through the area, the magnetic field lines that is passing, that is continuously changing. Means magnetic flux is changing. That is Faraday's law of electromagnetic induction. So now the flux will change, that's why there is an induced EMF, and that induced EMF will show the current here. So using the reverse of the motor rule, you can directly read, it will directly lead you to Faraday's law of electromagnetic induction. So when DC motor was first invented, Faraday's law was not invented at that time, but once DC motor is invented, then just its converse is the Faraday's law, and Faraday experimentally found that. Faraday thought that if I supply electrical energy and magnetic field is capable of converting it to kinetic energy, then instead of electrical energy, if I supply kinetic energy to the loop, then definitely magnetic field can convert this one into electrical energy. And that is the basis of the Faraday's experiment. Okay. Now, so this force we calculate F1 for this part, sorry, not F1, this one. So both are feeling the same force, so I consider this is F, this is also F, so net force 0, but the magnitude of the force is ILB. So in this case we consider that the current carrying loop and magnetic field, length of the current carrying loops and magnetic field are perpendicular to each other. If they are not perpendicular, there is an angle between L and magnetic field. Then it will be ILB sin theta only. So just write that general case. ILB sin theta. Here I consider perpendicular, then it is ILB. If it is not perpendicular, then it will be ILB sin theta. Then, force is there. What is the distance between the two line of action of the forces? Small v. See? Line of action of the forces are at a distance small v from each other, because forces are one on this part, another on this part. So what is the distance between them? That is the breadth of the loop, that is B. So to calculation of the torque, we can write it is force, either of the force into perpendicular distance. If there are two forces opposite to each other, how to calculate the torque? Either of the magnitude of the force into perpendicular distance, that is F into B. Then you can write this one as tau equal to F means ILB sin theta into B, ILB sin theta into B. Then can I write this one as ILB together into B sin theta. A into B is the area of this rectangular loop. So current into area will be magnetic dipole moment. So that is capital M. So from this we can calculate tau equal to MB sin theta. Okay? Means the vector form of the torque I can write tau equal to M cross E. The same form you derived in electric field, like tau equal to P cross E, means PE sin theta. Same for electric dipole present in an uniform electric field. Electric dipole present in an uniform electric field will experience only a torque, that is P cross E. Similarly here, M is considered as the magnetic dipole moment, so it is having a torque M cross B when present in uniform magnetic field. Same, exactly same as that of the electric field. Okay, now similar to the electric field, like potential energy we can calculate, that is minus P dot E. So you can also apply same thing here, magnetic potential energy minus M dot E. Just one-to-one correspondence. The other formulas for work done that you can write also, MB cos theta 1 minus cos theta 2, same. Okay. So in this way, whenever you are doing the study of a dipole, then there will be not that much difference between magnetism and electricity. If you are doing the cases of a dipole, because if you are going to study the presence of a single charge, that field we can define by Coulomb's law, but field of a single pole we cannot say anything because single pole does not exist. So there is a problem. But once you consider the dipole, then electricity and magnetism will become identical because both has the notion of the dipole. But in case of electricity, the electric dipole moment is defined by Q into D. Whereas in magnetism, dipole moment should be defined by current into area, not by pole strength into length, because pole strength is not a physical quantity like electric charge. Only this is the difference. If you properly define the dipole, then in moment magnetism by current into area of the loop, then the remaining theory is similar to electricity. Okay. Now, one more topic we will discuss, that is what happens to this Gauss's law in magnetism. Earlier we calculated closed integral E dot ds equal to Q enclosed by epsilon naught. Now we want to apply Gauss's law for magnetism. It will give nothing. Zero. Why? In the junior classes, class 4, 5, etc., 3, 4, 5, when students ask that, first they learn about magnet in science book. It is said that poles of the magnet cannot be detached. Why? What answer they learn? If I have a large bar magnet, I will break it into two parts. Then I will find two poles and these two parts. If I break this part, again I will get two parts which both of them are contain two poles. Then I want to break, and further whatever be the small part I will break, I will get, still it contains two poles, so we cannot detach it. That means magnetic single pole does not exist. But is this a proper answer? You are saying that I am breaking and the smallest part I will get, that will not contain and that will also contain 2 poles. What happens if you can't break further and I can break further? Suppose I am using a very high quality device which can break even further, then so the answer that is given to the students is valid only for those classes but not at the higher level. Means it is not depending on the ability how much small part you can break. The pole does not, single pole does not exist at all. So how to explain that? You cannot break further means pole will never exist. That is not true. First you have to draw the field lines. First you have to draw the field lines for a bar magnet. Suppose we consider a bar magnet. This is the bar, north, south. Now, how to draw field lines? This one. Check here. I will draw only 2. There are many more. And in the book, if you see, you will see some lines like this. Some lines like this. But don't think they are those open lines. Magnetic field lines are always closed. Means they are closed by this amount, and in the book that cannot be drawn because it will take too much space of the page. Okay, field lines are always closed loop. They are not like electric field lines which are open curve. Electric field line means start from positive charge, goes to negative charge, or goes to infinity. So magnetic field lines are not like that. They are, we can say that they are originating from the north pole and going to the south pole. We cannot say because outside the magnet they are going from north to south, but inside the magnet they are going from south to north. So they are closed loop. So what is their origin? Like electric field lines, I can say its origin is the positive charge. Its termination point is the negative charge. So similarly, what is the origin of magnetic field lines, or what is the terminating point of the magnetic field lines? Can anyone say? Closed loop. Means there is no single source of magnetism where the positive field line starts and where the field line ends. Means there will be no pole at all. Now, if we apply Gauss's law, closed surface. See, through this closed surface, this field line is entering, this field line is leaving. It is entering and it is going inside. Now it is also leaving. Check. The field line that goes into the surface, the field line that goes into the surface here, that field line will leave the surface. Similarly, for other field lines, if it goes into the surface, then it will definitely leave the surface. So what is the total flux through this closed surface? 0. So that's why Gauss's law in magnetism will provide 0. Means the amount of flux, that is the number of field lines going inside, will be equal to the number of field lines coming out. Always true. Because otherwise you have to consider that some field lines go inside and not coming out, or some field lines coming out and not going inside. Means there are certain source of field lines and there are no sources of magnetic field lines. Sources means there will be a single pole. So single pole cannot exist. That's why magnetic field lines are closed loop always. For a straight current carrying wire, what are the shape of magnetic field lines? Concentric circle, means again closed loop. So closed loop is the magnetic field line structure is always the closed loop, which will remind you that there is no source of magnetism. Where the charge, no positive source or negative source. Positive source means the pole from which the lines originate. Negative source means the point where the lines terminates. So this type of origin of magnetic field lines are not present. Means magnetic pole does not exist alone. So always you have to consider a dipole. And whenever a dipole is present inside a Gaussian surface, what is the net flux? 0. Because positive charge and negative charge total will become 0. So enclosed charge 0 means Gauss's law will give you 0. So flux is through a closed surface is always 0 for magnetic field. And that is confirms Gauss's law in magnetism. So if it is asked what is the main principle which Gauss's law of magnetism tells, it tells that magnetic monopole does not exist. Magnetic monopole does not exist. That is the main essence of the Gauss's law in magnetism. In case of electricity, it shows that E dot ds closed integral will be Q enclosed by epsilon naught, means the source of electricity exists. To create flux 0, you have to consider the positive and negative source by equal amount inside the Gaussian surface. But in magnetism, always there are equal amount of positive pole and negative pole present, means it starts from a dipole. Single pole does not exist. Clear? Now, there are some calculations of the magnetic field that we can, calculations of the electric field that we can do. We can use gas, in which we can use Gauss's law to find the field easily. Like infinitely straight wire, like infinitely straight surface, like spherical direct non-conducting volume charges. For all these problems, I can apply Gauss's law to solve it more easily. But here, I cannot find magnetic field easily by using Gauss's law, because Gauss's law will give you 0. In cases of electrostatics, by applying Gauss's law, in certain problems where there are symmetries, like cylindrical symmetry and all this spherical symmetry, I can find field easily than using Coulomb's law and integration. But here we cannot do. So that's why there is another symmetry argument which holds in case of magnetism, that is this one. Closed integral P dot dl mu naught I enclosed. This is called Ampere's circuital theorem. This is analogous to Gauss's law, which will help you to calculate the magnetic field if there is a symmetry. Previously, Gauss's law is a surface integral, this one is a line integral. Means it is integrated over a curve. V dot dl equal to mu naught I enclosed. This is Ampere's circuital theorem. Okay, now I will discuss only one calculation from this that is required as of now. That is, if I consider this one is a straight current carrying wire. If this one is a straight current carrying wire, I want to find the magnetic field at a perpendicular distance r from this wire. Perpendicular distance is r. Check. If I consider r at this point or at any distance r, will it be here, will it be here, will it be here, here, all these points? The magnetic field will remain same value at that point, because all are, this wire is the wire and at a distance r we are calculating. So we can consider that there is a circular loop over which at every point magnetic field will be same, because all those points of the circumference are at the same distance. So I can consider an Amperian loop. Previously we considered Gaussian surface. Now here we will consider Amperian loop. Like this. This one is okay. Now at each and every point of this imaginary loop, the field will remain same magnitude, and what will be the direction of the field? Always tangent to the loop, because straight wire magnetic field is like circular loop, circle, concentric circle. So at each point, if you draw the tangent, it will show the direction of the magnetic field at that point. So let us consider any arbitrary point here. So this is the direction of the magnetic field at this point. And what is the direction of the elemental length of this loop? Same. That is dl. So dl vector and b vector are always along the same direction at every point of this imaginary Amperian loop. Okay. Means this one is the wire, this is the circle. So at every point magnetic field and dl are along the same direction. Both are along the tangent. So angle between them is 0 degree. Then I can write for this b dot dl right here. So it will be b is constant. So b can be taken out. Cos 0 will be 1. Closed integral dl will be there only, equal to mu naught. What is the enclosed current? Suppose this wire carries a current I. Mu naught I by. Now closed integral dl means entire length of the Amperian loop, that is 2 pi r. See, the straight wire calculation is coming directly. Previously, in the last class, we have calculated this one by considering the finite wire formula and then letting the limit pi by 2. That is pi 1 plus pi 2 equal to pi by 2. We will get the same result by using Ampere circuit law. Okay. And remember here, in electromagnetism, when we apply this one, it is taken as the conduction current. But I enclose actually is the total current, not only the conduction current. It is conduction current plus displacement current. Conduction current as well as displacement current. So that is the Maxwell's modification of the Ampere's circuital law. That is in the part of electromagnetic wave. So we will discuss that later. Is it clear, all these things? So starting this portion, immediately start to read these portions and all these things, because these portions is much more difficult than electrostatics, because the directions are very confusing. Many times due to only direction you cannot find the correct answer.